This is video 15. In this video, we introduce the decomposition of a path in extremum arcs. We also present some basic properties and extend the previous definitions. Consider a B-infinite window W which is not a cycle. This window is in gray. The graphs G1 and G2 are the cut of the grid associated to W. Consider a simple path P whose first and last positions belong to the window W. This path is hatched. We will now build the decomposition of P in extremum arcs in the graph G1. This construction is done in 3 steps. In the first step, we remove all the positions of the path P which does not belong to G1. We regroup the remaining ones into arcs of G1. In this example, the path P is in white and the positions of P which belong to G1 are hatched. Now we regroup these positions into arcs. In this example, we obtain 8 arcs of G1. These arcs are maximal. For example, the arc A1 is the segment of P from the index 1 to the index 12. Remark that the segment of the path P from index 1 to index 13 is no more a subgraph of G1. We do not need the path P anymore. We only draw the 8 arcs. During the second step, we replace each of these arcs by the extremum arc extracted from it. In our example, only the first arc is not extremum. Let's modify it. Now the 8 arcs are extremum. During the third step, we remove the arcs which are dominated by another one. Here the arcs A1, A2, A3, A4 and A5 are not dominated. Thus we keep them. The arc A6 is dominated by A1, then we remove it. The arc A7 is dominated by A5, then we remove it. The arc A8 is dominated by A5, then we remove it. Finally, we obtain a sequence of 5 extremum arcs such that any of these arcs is consecutive to the previous one. This sequence of arcs is the decomposition of the path P in extremum arcs in the graph G1. This tool will often be used during microscopic reasoning. Now, we present some basic properties of this decomposition. Let's consider the previous decomposition. Remark that since the path P is simple, each arc of the decomposition is strictly consecutive to the previous one. Let's consider the dual decomposition of the window W according to the decomposition of P in extremum arcs. The previous remark implies that the length of a dual segment is at least 2. Now consider the window W' associated to the decomposition of P in extremum arcs. This window is in gray and we remind that it is made of the concatenation of the dual segments with the arcs of the decomposition. The graphs G3 and G4 are the cut of the grid associated to W'. Here is an important remark. Consider an arc of the graph 3 which starts in a dual segment DI and ends in a dual segment EJ. This arc dominates all the arcs of the decomposition from AI plus 1 to AJ. In this example, the arc A starts in D0 and ends in D4. Then this arc dominates the arc 1, the arc 2, the arc 3 and the arc 4. Now we aim to show that if position of the path P belongs to the graph G3, then it belongs to the window W'. To show this result, for the sake of contradiction, consider a position U which belongs to both the path P and the graph G3 but does not belongs to the window W'. We remind that the extremities of the path P are in the window W and that the window W is a subgraph of G4. Then there exists an elementary arc A of G3 such that the arc A passes by the position U and is a subgraph of P. We now list the different possibilities according to the position of these extremities. Here we represent and hatched a part of the arc A where its extremity intersects within another arc of P. In this case, the arc of the decomposition which intersects with the arc A is hatched. Thus, the path P is not simple. Then the extremities of the arc A must belong to a dual segment. Now, an extremity of the arc A intersects with the extremity of a dual segment. In this example, the arc A2 of the decomposition should have been longer. Now, if the extremities of the arc A are in two different dual segments, then it dominates an arc of the decomposition. In this example, the arc A starts in the dual segment 0 and ends in the dual segment 1, then it dominates the arc A1. This fact contradicts the definition of a decomposition in extremum arcs. If both extremities belong to the same dual segment, then this arc should belong to the decomposition in extremum arcs. Here the hashed arc should be the arc 0 of the decomposition. Finally, we can conclude that the hashed area is devoid of any position of the path P. This remark is useful later to find an area of the grid free of any tiles of the path assembly or of the seed. This area will be used to create new path assemblies without fearing inconsistency. Here we represent a path P in white. Another interpretation of this lemma is that any position of the path P which belongs to the graph G1 also belongs to the interior of an arc of the decomposition. We now introduce positive decomposition. Until the end of this video, we will give a lot of definitions. We will discuss the importance of these definitions in the following video. First, we need to introduce positive or negative dual segments of the windows. Consider a finite dual segment DI, that is to say that I is between 1 and L-1. There exists two indices J1 and J2 such that the path P at index J1 is the first position of DI and the path P at index J2 is the last position of DI. The dual segment is positive if and only if J1 is less than J2. For example, consider the dual segment D1. This path is hatched. The first position of this dual segment is also the position P1 and its last position is also the last position of the path P. Then the dual segment D1 is positive. Consider another example. The dual segment D4 is hatched. Its first position is also the position P103 and its last position is also the position P98. Then the dual segment D4 is negative. Now, we extend the notion of positive or negativity to arc of length 1. Remark that being an arc of length 1 is equivalent to being an arc of width 0. Consider the arc A2. This arc is hashed and the path P is in white. The unique position of this arc is the last position of the path P and also the position W32. Consider the last time where the path P intersects with the window W. This position is the position of the window W at index 104. Since 32 is less than 104, then this arc is negative. Here is a quick remark. Consider the following path P'. Remark that P is a subgraph of P'. Here the arc A2 is no more of length 1 and is positive. Thus the orientation of an arc of length 1 may change depending on the path we consider. Now, we consider an arc of length 1 whose unique position is also the position of the path P at index J1 with J1 different from 1 and the size of P. This position is also the position of W at index I1. Then consider the following neighborhood of this position. This position has four neighbors, Wi1 plus 1, Wi1 minus 1, Pj1 plus 1 and Pj1 minus 1. Since P and W are simple and since the length of the arc is 1, then these four positions are all different. Moreover, the two edges of P must belong to the graph G2, and thus to the right side of the window. Then locally, the window W is a corner and we can consider that Wi1 minus 1 is west of Wi1 and that Wi1 plus 1 is north of Wi1. Then only two cases may occur. In the first one, Pj1 minus 1 is south of Pj1 and then Pj1 plus 1 is east of Pj1. In this case, the arc A is positive. In the second case, Pj1 minus 1 is east of Pj1 and Pj1 plus 1 is south of Pj1. In this case, the arc A is negative. For example, the arc A6 is positive. The arc A7 is also positive. This pattern matches the one of the left up to rotation. Now a decomposition in extremum arc is positive if and only if all its arcs are positive and all its dual segment are positive. Intuitively, A decomposition is positive if its arcs appear in the sequence in the same order than the one of the path P. For example, consider the order of the path P. Arc A1 is its first arc. The arc A5 is the second one, thus the decomposition of P is not positive. Arc A4 is the third one. Arc A3 is the fourth one. And arc A2 is the fifth one. Later, we will work mainly with a path P whose decomposition in extremum arcs is positive. In fact, the main result of the toolbox is that the decomposition in extremum arcs of a positive extremum arc P is positive, but we need some technical results before proving this one. Now we extend the definition of interior to dual segment. Consider a finite dual segment DI, thus I is between 1 and L-1. Then there exists two indices J1 and J2 such that Pj1 is the first position of the dual segment DI and Pj2 is the last position of the dual segment. Then the segment of P from J1 to J2 is basic. The interior of the dual segment D1 is the interior of this basic segment of P. In this example, we consider the dual segment D1. In this special case, the interior of D1 is the interior of the path P. Here we have drawn a window W in white, the window of the interior of D1 is in gray and the interior of D1 is hatched and the path P is hatched in the other direction. Now we compute the interior of the dual segment D2. Here the basic segment of P associated to D2 is hatched, the path P is in white. Here the interior of D2 is hatched, its window is in gray. Now we compute the interior of the dual segment D3. Here the basic segment of P associated to D3 is hatched. Here the interior of D3 is hatched, its window is in gray. Now we compute the interior of the dual segment 4. Here the basic segment of P associated to D4 is hatched. Here the interior of D4 is hatched, its window is in gray. Now we define the interior of D0 and DL. In fact, these two dual segments have the same interior. Consider the window W second associated to the path P. The interior of D0 and DL is the graph G6 which is the right side of W second. We discussed the interaction between all these parts in the following video.